For a long time, we imagined a very specific address for life in the cosmos. We called it the habitable zone, or more playfully, the Goldilocks zone. This is the region around a star where the temperature is just right, not too hot, not too cold, for liquid water to exist on a planet's surface. We pictured Earth-like worlds with blue oceans glistening under the light of a friendly sun. This idea has guided our search, pointing our telescopes toward distant stars, looking for planets that fit this narrow, comfortable profile. It was a beautiful and simple starting point, a cosmic story we could all understand based on the only life we've ever known, our own. But the universe, as it so often does, has proved to be far more imaginative than we are. The Goldilocks zone is a wonderful concept, but it's fundamentally a human-centric one. It assumes that all life needs surface water and direct sunlight, just like we do. It's a bit like searching the entire world for car keys but only looking under the streetlights. What if life doesn't need a sun-drenched beach? What if it thrives in the crushing dark, warmed by forces we're only just beginning to appreciate? The cosmos is vast, and its rulebook is likely filled with exceptions and possibilities that challenge our terrestrial assumptions at every turn. To find our cosmic neighbors, we have to broaden our perspective. We must be willing to look in the cold, the dark, and the seemingly inhospitable corners of space. Our own solar system offers the first clues to these new exotic addresses for life. Journey with me to Jupiter, the colossal king of planets. Orbiting this gas giant is a small, icy moon named Europa. From a distance, it looks like a quiet, frozen cue ball, crisscrossed with reddish-brown cracks. It's far, far outside the sun's habitable zone, a place so cold that any surface water would be frozen as hard as rock. But beneath that thick, icy shell, scientists believe there lies a vast global ocean of liquid saltwater. So how can this ocean stay liquid in the freezing depths of space? The answer isn't sunlight, it's gravity. As Europa orbits Jupiter, the giant planet's immense gravitational pull constantly squeezes and stretches the moon. Down in that dark, sunless sea, hydrothermal vents, much like the ones on Earth's ocean floors, could be spewing out heat and chemical nutrients. It's a perfect recipe for life, completely independent of the sun. And Europa isn't alone. Fly out to Saturn, the ringed jewel of our system, and you'll find a tiny moon named Enceladus. This little world astounded us when our Cassini spacecraft saw something incredible. Giant geysers of water vapor and ice crystals erupting from its south pole, blasting hundreds of miles into space. These plumes are direct evidence of a subsurface liquid ocean, also warmed by the tidal forces of its parent planet. We've even tasted these plumes, and they contain water, salts, and organic molecules, the very building blocks of life as we know it. These ocean worlds have completely redefined our search for life. They show us that the ingredients for biology can be found in the most unexpected places. Life might not need a sky, it might just need a sea. It doesn't necessarily need a gentle sun. A powerful planet next door will do just fine. These icy moons are no longer seen as desolate wastelands. They are now prime candidates in our cosmic quest, compelling us to imagine ecosystems that thrive in eternal darkness, powered by the rhythmic pulse of gravity. The power of an atmosphere can be just as potent as a star's light. Think of Venus, Earth's celestial neighbor. It's much closer to the sun, but its scorching surface temperature isn't just due to its location. It's the result of a runaway greenhouse effect, where a thick, suffocating blanket of carbon dioxide traps heat relentlessly. Now imagine a planet much farther from its star than Earth, out in the cold fringes of its solar system. If that planet had a super thick atmosphere, rich in greenhouse gases, it could trap whatever little heat it receives and create a warm, stable climate on its surface, even in the dim twilight. This opens up a whole new class of potentially habitable worlds. Consider a super-Earth, a rocky planet larger than our own. Its stronger gravity could hold on to a much denser atmosphere for billions of years. Some of these worlds might be eyeball planets, tidally locked to their star, so that one side perpetually faces the light and the other remains in eternal darkness. On the day side, a vast ocean might be vaporized, while on the night side, it's frozen solid. But in the twilight zone between these two extremes, a permanent ring of temperate, life-friendly conditions could exist. But what if a planet had no star at all? The universe is filled with them, nomads, drifters kicked out of their home systems during their chaotic formation. We call them rogue planets. They wander the cold, empty darkness between the stars, seemingly the most desolate places imaginable. Yet, even here, life might find a way. A sufficiently massive rogue planet could generate its own heat from the decay of radioactive elements in its core, a process that happens right here on Earth. If that world also managed to hold onto a thick hydrogen atmosphere, it could insulate itself, creating a surface warm enough for liquid water. Life on such a world would be unlike anything we could imagine. It would exist in a world without day or night, without seasons, and without a sun in its sky. Our journey into the cosmos is just getting started, and our tools are getting sharper. The James Webb Space Telescope and the observatories that will follow are giving us the power to not just find these distant worlds, but to study their atmospheres. We can now look for biosignatures, chemical fingerprints in the light that passes through a planet's air. We're searching for the telltale signs of biology at work, like the presence of oxygen and methane in the same atmosphere, a combination that on Earth is a clear indicator of living processes. It's cosmic detective work on the grandest scale. This new era of exploration requires new ideas. We're moving beyond the simple concept of a habitable zone and developing more complex models that consider a planet's geology, its atmosphere, and its relationship with its host star, or even its parent planet. We're learning to think like cosmic biologists, considering life that might be based on different chemistry, perhaps using methane instead of water as a solvent on frigid worlds like Saturn's moon Titan. Every new discovery, every strange new world, expands our imagination and refines our search. The coming decades promise a revolution in our understanding of our place in the universe. With each new exoplanet cataloged and each atmosphere analyzed, we gather another piece of the puzzle. Will we find microbes in the plumes of Enceladus? Will we detect the breath of a forest on a super-Earth light years away? Or will we find something so completely unexpected that it rewrites our textbooks entirely? The sheer number of potential habitats, trillions of planets in our galaxy alone, suggests that the odds are in life's favor. The cosmos beckons. It calls us to look up and wonder, to chase the light of distant suns, and to listen for the faint whispers of life across the vastness of space. We are the generation that has the tools and the vision to undertake this search in earnest. The universe is under no obligation to make sense to us, but it has given us a mind to try. And as we continue to explore its wildest, most unexpected corners, we may find that we are not and have never been alone. The greatest adventure of all awaits us.